So after looking at the camera post-estimation algorithm for an uncalibrated camera where the intrinsics of the camera is unknown, let's move on to look at calibrated case where the camera intrinsics value k is known. Since k is made up of the focal length as well as the principal points. So this simply means that the focal length and the principal points are known in this particular case. And what I'm going to talk about would be three different approaches that was actually invented over the past about 150 years time span. And since I'm taking them from three different papers, in contrast with the first work that I spoke about in uncalibrated camera that was taken from Richard Hartley's textbook, please bear with me that there will be a slight overload of the denotations of the parameters in the subsequent approaches because I'm simply following the notations in the original paper. In the case of a calibrated camera, usually the approaches are following a two-stage approach to solve the perspective endpoint post-estimation problem. And in this case, the camera intrinsics is known. So in the first step, we will first solve for the unknown depths. Suppose that we have three 3D points denoted as P1, P2, P3. So note that this notation here differs from the previous notation where I use capital X1, X2, X3 because I'm following this particular paper that document this particular approach. Actually, it was not proposed in this paper. This approach was proposed in 1841. That was about 150 years ago by a photogrammetrist, and he proposed this particular approach. So the notation here, I'm following that paper, and it denotes the 3D point as P1, P2, P3, and the camera center is here. So let's denote this camera center as P, for example. So S1, the first depth here, it's the magnitude of the vector from P, the camera center, to P1. And S2 would be similar from P to P2. And for S3, it will be P to P3. So these depths are unknown. What we are given would be the points, these 3 points with respect to the world frame, as well as the observed image points, which I will define later in this particular formulation. So the first step would be to compute this unknown depths. And what it means here is that once we have computed the depth, suppose we further denote these points P1, P2, P3 as in the world frame, for example. Let's just use a superscript here. And after computing the unknown depths, what we will get is that we will get the corresponding 3D points that are defined in the camera frame. So I'm going to denote this as P1C, P2C, and P3C, for example. Then once we get these two sets of 3D points, of course, the first set is given. The second set is what we compute from the unknown depths S1, S2, S3. So once we get this, we'll be able to simply align these two frames because these 2 points are actually referring to the same 3 points in space. But the first set here is defined according to the world frame. And the other set here, the second set here, is defined according to the camera frame. So what we are trying to do here is that given these two, after we have solved for the unknown depth, where we can do what we call the absolute orientation algorithm to solve for the rotation and translation that aligns these two reference frames. Now, we know that the unknown digit transformation between the two frames, it's parameterized by a rotation which has 3 degrees of freedom. So this guy here has 3 degrees of freedom, and a translation which also has a 3 degrees of freedom. So we look at rotation. In the minimal representation is a Euler angle, the rho, pitch, and yaw angle. Hence, there's 3 degrees of freedom. So T, it's with absolute scale. So there's Tx, Ty, and Tz. Tx, Ty, and Tz. Hence, there's 3 degrees of freedom here. In total, there are altogether 6 degrees of freedom that we need to solve for in the unknown rigid transformation. And we also know from the previous uncalibrated case that each point correspondence gives two independent constraints. So as a result, because we are directly solving for the rotation and translation here, in this case where the intrinsic value is known, so altogether we will need 3-point correspondences to as a minimal set of correspondences to solve for the 6 degree of unknowns in our rotation and translation over here. Hence, we are going to look at the solution for this using the 3-point correspondences. It was invented by this guy Grunet, a German scientist in 1841. That's about 160 years ago. So this is also otherwise known as the P3P formulation, the perspective 3-point algorithm, which it makes use of the minimal set of correspondences, which is 3-point correspondences, to solve for the camera post estimation problem. And here, let's denote the 3 points as P1, P2, P3. At each point here, the inhomogeneous coordinate is given by xi, yi, and zi. Given this set of 3 points, we can compute the distance between any pair of points. So altogether, since we have 3 points, 3 choose 2 is going to give us 3. And this means that we have altogether 3 sides to compute the length. And let's denote the sides as A, B, and C, where A is the distance between P2 and P3, B is the distance between P1 and P3, and C is the distance between P1 and P2. So this can be simply taken by the norm of the difference between the two vectors of that represents any two of the points. And we further denote the corresponding observed perspective projection. So P1, P2, P3 are defined earlier on as the 3D points. And we know that these 3 points, the 3D point P1, P2, P3, are going to be projected onto the image as 3 image point here, which we will call Q1, Q2, and Q3 over here. So each one of this Qi, denoted by Qi, is simply represented by the inhomogeneous coordinates of Ui and Vi, which means that it's the image pixel location. And we know that since the camera intrinsics is known, this means that this 3x3 camera intrinsics is known. It also means that we also know the focal length as well. So if we treat the principal point Cx and Cy equals to 0, that means that the center of reference frame is in the middle of the image. We can applying this focal length on the 3D point. This means that by multiplying k with p to get q, this is what we get in terms of inhomogeneous entry of Q. We will simply equate Ui equals to F multiplied by Xi, where Xi is the 3D point x-axis divided by Z. And similarly for Vi, it will be equals to F multiplied by Yi divided by Z. And then from here, we will be also able to get the unit vector from the camera center to the observed point. This is this guy over here, where this is the camera center, and if I observe this point here, which I call Qi, so what we can do here is that we can compute a vector using the homogeneous coordinates over here that is represented by Ui, Vi, and F, where F represents the focal length, divided by the norm of this homogeneous coordinate. And this is simply going to give us the vector which we denote as Ji, that's pointing in the direction of the image coordinate of Qi. Having found the unit vector that represents the direction of each light ray over here that we denote as J1, J2, as well as J3, we can move on to find the angle between any pairs of light ray. For example, in this case here, we denote the angle between J2 and J3. That means that it's this angle over here as alpha. And alpha here, the cosine of alpha can be found from the dot product of the two unit vector, which we denote as J2 and J3, that was computed earlier here in the previous slide. So we can do the same thing for the other two angles that is created by other two pairs of unit vectors that represents the light ray, and we denote it as beta and gamma. So now let us further denote the unknown distances between the point P1, P2 from the center of projection here. We will further denote this length, the length of this vector, as S1, S2, S3. So S1 represents the length, the magnitude from the camera center to P1. S2 represents the magnitude of the distance from camera center to P2, and S3 represents the magnitude of camera centers to P3. So we can then denote pi as equals to the magnitude, the scale, the unknown depth multiplied by the unit vector in the direction of that particular point. So in this case here, pi is actually a known entity because we are given the 3D point in the world frame, and j here, it's also a known entity. J here, it's known because we know the 2D correspondence, and this is the image point ui and vi, and we also know the camera intrinsics value, which also means that f over here, the focal length, is also a known entity. This means that in this case, we have an equation which consists of the unknown of Si, and putting everything together, we'll get these three equations by the law of cosines. So if I were to do two of the light rays, which point from the camera center here, for example, to the point of P2 and the point of P3, this actually forms a triangle that looks something like this. And we have denoted the angle made by these two rays as alpha in the previous slide. So cosine alpha is given by J2 dot with J3, which I have defined earlier on. And we also know that according to the law of cosines, so the cosine rule for a triangle, this cosine alpha can be expressed in terms of the length of all the three sides. And we also know from before that since these 2 points are known, this also means that the distance between these 2 points, which I have denoted earlier on as A, is also known. And the two sides, which the magnitude would be denoted by S2 and S3, would be an unknown. So where cosine alpha here is a known value, and A here is also known. So these two here are known from the triangle, and the unknowns here would be in terms of S2 and S3, which are the depth. So we can do this for the other two triangles that are created by the other pairs of points, namely P1 and P3. So here the angle here would be beta, and we can do the same thing. So cosine beta and this the distance between P1 and P3, they are all known, and the unknown here would be S1 and S3. Similarly for the third pair, where it's the angle between the 2 points of P1 and P2. So we know that the distance here, which we call C, is known, and whereas the depth here, S1 and S2, are unknown. And the cosine angle here, which we call gamma, these two values here, they are known values. And the unknown here, S1 and S2. And as a result, we get three equations over here and three unknowns, which we can then solve for the three unknowns using these three sets of equations. So in the original solution that was proposed by Grunet in 1841, he suggested that we'll introduce two auxiliary variables, which is called u and v, and then we will represent S2 in terms of u multiplied by S1 and S3 in terms of V multiplied by S1. So now with S2 represented as S in terms of S1 and U, and S3 represented in terms of S1 and V, we can substitute this back into this equation to replace S2 and S3. And as a result, we will get the three equations in terms of S1, U, and V. And these are the three equations that we get as a result. For each one of these equations, we can further reorganize it such that we make S1 the subject. And consequently, we can make use of these equations here to eliminate away S1. And by simply equating the first two equations and then the next two equations to form two equations in terms of the two unknowns u and v. Since we have two equations, two unknowns now, the problem becomes much more easier to solve, where we can simply eliminate u. Doing elimination, we can eliminate u from these two equations by making u the subject and then substitute it from equation 6 and substituting it to equation 7. We'll get a 4-degree univariate polynomial that looks something like this in terms of the only unknown. So now it's down to one equation and one unknown, where the unknown is actually v, one of the auxiliary variables that we have introduced earlier on. So, and the coefficients here, I'm not going to go through the derivation of the coefficient, but you can, if you are interested, you can work this out and verify that these coefficients here are all correct. It looks pretty complicated over here. So once we have the 4-degree polynomial that we have seen earlier on here in this slide, now the objective is to solve this 4-degree polynomial for the unknown variable v, which will give us up to 4 real solutions, because it's a 4-degree polynomial. So one way to solve this is to use what we call the companion matrix, where the companion matrix of a 4-degree polynomial is given by this particular matrix over here. So this is the companion matrix of a 4-degree polynomial, which is in this form over here, where the coefficients are simply a4v to the power of 4 plus a3v to the power of 3, all the way until a0 equals to 0. So we'll just simply substitute these coefficients into the last column of the companion matrix. So I'm not going to show the derivation of the companion matrix here, but we'll see this merely as a tool for us to solve a 4-degree polynomial equation. And once this is formed, what we can do here is that we take the eigenvalues of this companion matrix, and interestingly, the eigenvalues of the companion matrix gives the roots to the 4-degree polynomial. Since this is a 4 by 4 matrix, there will be altogether 4 eigenvalues, which denotes the 4 solutions. And this simply implies the 4 solutions to our 4th-degree polynomial. And once we get this 4 solution, we'll substitute each one of these 4 solutions. We'll retain the real solutions and then substitute these solutions for v back into equation 7 here. Since we know v already, there's only one unknown, which is u over here. We can substitute every one of the roots of v back into this equation to solve for u. We'll get a set of 4 solutions for the pairs of u and v's here. Then finally, once we are done with this, we can substitute it u and v here back into equation 5, which is shown here, to solve for S1. And once S1 is known, since we know an S1 and v, we can proceed on to solve for the remaining unknown, which is S2 and 3. So what this means is that by this step over here, we have gotten the unknown depths S1, S2, and S3. And now, what it means here by solving for the unknown depths is that since we know the unknown depths with respect to the camera center, this is which is denoted by FC over here, and S1, S2, S3 are the magnitude of this vector over here. So I represent this as S1, S2, and S3 as seen earlier on. And we also know that the directional vector, this directional vector can be computed from the image correspondence, which is given by the unit direction vector is J1, J3 in this case, and then J2 in this case. With this known depth right now, after solving the first step, we can compute the 3D points in the camera coordinate frame as Pi prime equals to Si multiplied by J. So this would be the 3D points defined in the camera frame. And now the next step would be, given this set of 3D points that is defined in the camera frame, uh, as well as the set of 3D points that were defined with respect to the world frame, we want to find the relative transformation between the camera frame and the world frame such that we align these two frames, and that would be given by a rotation matrix as well as a translation vector. And this problem can be formulated into a optimization problem given by this cost function over here, where we want to transform the Pi prime, which was represented in the camera frame. So after the transformation here, we are simply transforming P prime from FC into the world frame. And what we want to do here is that after the transformation into the world frame of P prime, we want it to match up with the original 3D points that was given in the world frame. So we want to minus this the distance away, and we want to minimize the total error in terms of this alignment error over here over the unknown rigid transformation parameterized by a rotation matrix as well as a translation vector. And we'll achieve this using what we call the absolute orientation algorithm. And note that although Grunet algorithm is developed for 3-point correspondences, the absolute orientation algorithm, it works for 3 or more point correspondences. So the first step to absolute orientation algorithm would be to remove the translation uh, between the two sets of points defined in the two different reference frames, P prime and P respectively. So the way to remove this would be first to compute the centroid of the respective set of points. Suppose that we have 3 points over here that is represented in the world frame, and I call this Pi, every single point as Pi, and I have another set of points which is represented in the camera frame. I represent it as Pi prime, every single point. So the first step here is to compute the centroid of Pi, and which I denote as Pi bar over here, and that's given by this equation over here. We simply sum out every entries in the point and divide it by the total number of points in this particular set. We'll do the same thing for the 3D point defined in the camera frame, and to compute the centroid, which we denote as Pi prime bar over here, and that will sum up all the points, the coordinates of all the points divided by the total number of points. Then the next step here, since we want to align this axis here with respect to its centroid, what we will do here is that we will just subtract the every point with the centroid to do a translation of this frame to its centroid. We'll apply the same thing for the 3D points expressed in the camera frame. We'll just subtract the every point with the centroid to move this frame here to the centroid. So after removing the translation vector from the 2 points, the only thing that remains in the 2 points would be the rotation matrix. And the next step here would be to compute the rotation matrix between the 2 points. We can do this by first computing a matrix M. This is actually a 3 by 3 matrix by simply summing up all the product of the points after removing the translation. So this here, it's actually the point in the camera frame, which is a 3 by 1 vector. And so the first Ri prime, this is in the camera frame. Ri transpose here is in the world frame. And this is 1 by 3 entries over here. So the product of these two, 3 by 1 multiplied by 1 by 3, it's going to give us a 3 by 3 matrix. And for every point over here, we will get a 3 by 3 matrix. We'll simply add up every entries. So first point, we'll get a 3 by 3 entries. And then second point, we'll get another 3 by 3. We'll add up every corresponding element of this to get the matrix M. So after we get the matrix M, we'll proceed on to compute the rotation matrix, the 3 by 3 octagonal rotation matrix, using the product of M with square root of Q inverse, where Q here is given by the product of the M transpose by itself. And then finally, once we have computed the rotation matrix, we can go back to compute the translation vector by simply aligning the two sets of points after we have compensated the rotation in the first set of points. And more specifically, the way to compute the square root of uh, the inverse of Q would be to make use of the eigenvalues and eigenvectors. So because this is a 3 by 3 square matrix that is given by this equation over here, M transpose multiplied by M. It's actually also a symmetric matrix because it's equals to this M transpose multiplied by M. Computing this would the SVD of this guy, Q over here. The left and right now orthogonal matrices would be the same. So it would be something like this: V sigma V transpose, where these V's are the same. And here, sigma over here would be given by in following this notation, lambda 1, lambda 2, and lambda 3. Because it's a 3 by 3 matrix, there's three singular values over here. And in order to compute the inverse of the square root, what we will simply do is that we will compute the inverse of the square root of the respective eigen values in sigma, and then putting it back into this equation over here that we pre-multiply and post-multiply by v and v transpose over here to get back this particular square root of the matrix over here. So after we have solved for the unknown camera pose using the Grignard formulation, which is the 3-point algorithm that we have seen earlier on, the next thing that we are going to look at is the degenerate configuration of this camera pose estimation problem under known intrinsics value. So we have looked at earlier on that to solve for the unknown camera pose, we took a two-stage approach, where in the first stage we are solving for the unknown depths of S1, S2, S3 using these three equations over here. So here, these three equations, it can be rewritten into the three polynomial equations over here: f1 xyz, f2 xyz, and f3 xyz equals to 0, where xyz here represents the camera center. So we have seen earlier on that this is the case. We have 3 points, p1, p2, and then p3 over here. So we are going to represent the camera center here as x, y, and z. And s1, s2, s3 here, and s2 represents the magnitude of the vector from the camera center to the respective points. So in the previous case, we see this S1, S2, S3 as unknowns, but we can also look at it from another perspective where we can keep this S1, S2, S3 as a fixed value, where now the unknown becomes XYZ, which is in fact what we are solving in the second stage when we solve the rotation and translation, where these two values here, the rotation and the translation, in fact gives us the camera center. And now we can reparameterize this in terms of the unknowns from S1, S2, S3 to XYZ, which represents the camera center. And I'll skip the full derivation here because it's very complicated. So we'll just take it as that this can be reparameterized into a set of system of three polynomial equations in terms of the inhomogeneous coordinates of the camera center here. Then, without a loss of generality, so suppose that we want to find the solutions to the set of system of polynomial equations, which is written in a general form. Suppose that we have n unknowns here in the system of polynomial equations and n equations, where I have f1 all the way to I have f1 that's in the function of this all the way to fn over here. So in the context of our 3-point algorithm that we have seen earlier on, this would be simply just three equations and three unknowns where with x, y, z. So without a loss of generality, suppose that we wish to find a set of n unknowns, which we denote by x1, x2, all the way to xn, by the set of n equations in the form of fi over here, where I equals to 1 to n. That means that I have a system of polynomial equations f1 that's parameterized by the set of unknowns x1 to xn, and all the way to n fn that's parameterized by the same set of unknowns over here. We say that this particular system of polynomial equation we say that the solution is non-degenerate, or the solution is stable if we were to make any perturbation to the function by any of the variables, unknown parameters here. So in terms of this, fi over a small perturbation of x1, for example, then this should not give rise to a change in the value of dx1. In other words, dx1 should remain as equals to 0 for the system to be stable. And this can be rewritten as a system of homogeneous linear equation, where the first part here is represented as the Jacobian, which is the first derivative of the respective equation over here with respect to all the respective unknowns in the equation. And the second part here is simply the small change in the respective equation. So this can be derived from the equation, where we have first we start off with a system of polynomial equation. Say for example, fi x1 all the way to xn equals to 0. We can derive this using what we call the total derivatives. And this is given by partial differentiating fi with respect to dt, for example, auxiliary variable. And this would be equals to the partial derivation of fi over the first unknown variable in fi multiplied by the partial derivation of this x1 over dt. So this is following the chain rule, plus all the way until we differentiate fi to delta xn and delta xn divided by delta t. So after we get this equation over here, we can see that delta t appears on all the terms on both of the left hand side and the right hand side. We can cancel off delta t here, and what we are left with would be delta fi equals to delta fi over delta x multiplied by delta x1 plus all the way until delta fi over delta xn multiplied by delta xn. And we can rearrange this equation into this metric form where fi equals to f1 all the way to fn. If we perturb this equation with any one of the unknown variable, it shouldn't make any change to the final solution, which is denoted by x1, x2, x3. So dx1 means that the change after we perturb the individual equation with the respective unknown variable. So in this case, if there's zero change here, that means that this guy here, the solution to this, because this can be seen as a homogeneous linear equation, ax equals to 0. After we solve for this guy here, uh, the only solution for the vector here should be 0. That means that it must be a trivial vector. If there is other solution here, what this means is that a perturbation of the function over here would lead to a whole family of solution, or will lead to some unstable solution in our unknowns. And we can use this to check whether what are the degenerate configurations on our 3-point algorithm that was developed by Grunet in 1841. So we saw earlier on that the three equations here, equation 1, 2, and 3, can be rewritten into a system of three polynomial equations in terms of the inhomogeneous coordinates of the camera center xyz. And following the total derivatives that I have briefly talked about just now, this step over here, we can actually take the partial differentiation, the total derivatives of every one of these equations, and then rearrange it into this form over here. So this is what we will get. I'm not going to derive this because it's pretty complicated, and this results here is directly taken from the paper. We can see that we can call this as our M matrix here, which is 3 by 3, and this is the dx, dy, dz that we have seen earlier on. So we can see that the polynomial equation here, f1 is always going to be equals to 0, f2 is also going to be 0. What this means is that if we take the small change in f1 here, it better also going to be 0, and hence we can form a homogeneous linear equation over here where A is given by this matrix over here. It's simply the difference between the camera center, the respective coordinate of the camera center with the respective coordinate of the individual 3D points, x minus x1 and so on and so forth. And B is a function of s1, s2, s3, as well as cosine alpha, cosine beta, and cosine gamma that we have saw earlier on. So we can see that in this particular case here, for degeneracy to happen, a small perturbation here which will lead to a non-trivial solution here is going to be given by the case where M is rank deficient. And we will go on to show that in the Grunet formulation, there are two cases of degeneracy that can be observed. The first case is that the 3 points P1, P2, and P2 and P3 here, they are collinear. What this means is that the 3 points are sitting on a straight line, collinear, and in this case, the configuration is degenerate. And the second case of degeneracy here is that the camera center and the 3 points lie on a plane, which means that they are coplanar, because any 3 points will always form a plane. P1, P2, and P3 will always form a plane. This means that P, the camera center, is also lying on this particular plane, and this is going to be degenerate. So in the first case, when the 3 points are collinear, we can illustrate it using this illustration over here. So P1, P2, P3, they lie on a straight line. This means that they are collinear, and P here can lie anywhere which we simply denote it using this point over here. So if we were to look at this case, because P1, P2, P3 forms a line, so no matter where P3 is lying at, it's always going to form a plane with all the other the three given points here. So in this particular case, what we can see here is that we can define a world reference frame here, for example, such that the XY plane here is on the plane that is formed by these 4 points over here. And what this means is that if we look at the A matrix over here, because the A matrix is simply the difference between the respective uh, entries in our camera center with the respective entries in the 3D point, we can see that the last column here vanishes because when the XY plane of the world frame aligns with the plane that is formed by P and all the other 3 points, they would all have the same Z coordinates. And this means that the last column here becomes 0, which means that this A here is going to uh, become rank deficient. And this is not good because what it means here is that after we put this A matrix back into this equation over here, since this is already rank deficient, uh, the multiplication of a rank deficient, even with a full rank matrix, would end up to be a rank deficient matrix of M over here. So what this means is that now we would have a rank deficient M matrix that leads to a non-trivial solution of dx, dy, and dz. And this means that if we were to perturb the equation, we will end up with a family of solution. We can also observe similar problem as the previous case when the camera center lies on the plane that is formed by the three 3D points that were given to us. And in this particular case, as illustrated in this figure over here, so all the 4 points here, P1, P2, P3, and P, which is the camera center, they form a plane. We can, similar to the first case, we can also assign a world frame such that the XY plane over here it's aligned with this plane. And what this means is that the z coordinates of all the points would become the same, and the last column here in the A matrix would become 0. And this means that A becomes rank deficient, which also causes the M matrix over here to become rank deficient. And as a result, we'll get a non-trivial set of solution for dx, dy, dz, and this means that configuration becomes degenerate.